Hello everyone, welcome to this video. In this video, we'll be solving this question which states that if G be the symmetry group of the given circle, then we have to show that G has elements of every finite order as well as elements of infinite order. Right? So first of all, let's examine this symmetry group of circle. So what is the symmetry group of circle? It is nothing but a generalization of the dihedral group that we study for polygons, correct? Regular polygons. So I may write it as a generalization of dihedral group of polygons, right? So if this is that, then that means it contains two kind of elements within it. It has infinite number of reflections present within it. Let me tell you why. And there are infinite number of rotations present within it. Why? Because there are infinite number of members within it. So if you look at a circle here, correct? So and we can have it here also, correct? So for this particular circle, you can have reflection along many axes because you can have the reflection along all exactly all the diameters of this circle. So there are infinite diameters for this circle, hence we may have reflections through these infinite number of diameters, correct? So these are basically infinite in nature, correct? So in a similar manner, you can rotate it, infinite reflections are there, right? So in a similar manner, if this is the center of the circle and this is the initial point P, so you can rotate the circle by 0 degree, by 0.5 degree, 1 degree, 2 degree, 3 degree and so on. So whenever you move it, you have the same orientation, hence you have that rotation give you the symmetry element, hence it has infinite rotations within it, right? Now they are asking, we need to show that this group G has elements of every finite order as well as elements of infinite order. So when we talk about reflections, so we know when you perform the reflection twice, you get the identity element. So if we have the reflection as F, so F composed with F give you R0, which is the identity element, correct? If this is the identity element, you know when we perform the reflection twice, we obtain the identity elements, hence the order of every reflection is 2, correct? Okay. So that means we have an element, we have in fact very many elements, all the reflections which have order 2, right? But they are asking to us that every finite order. So that means the other elements should also have order 1, 3, 5, 4, 6, 7, 10, 50, 100 and so on, correct? So therefore, let's talk about the order of rotations here, correct? So here, if we take a rotation about 90 degree, what would be its order? Can you think of it? When you rotate this circle by an angle of 90 degree, right? So you first of all move it by 90 degree, correct? Then by 90 degree, then by 90 degree, and then by 90 degree. So after 4 such reflections, you get back to the original position, correct? This is the original position. Hence in this particular case, you have R90 into R90 into R90 into R90. This give you what? R0, right? Hence we say the order of R90 is 4 in this particular case. So we have an element of order 4, which is a rotation. Similarly, if you take any other, if you take in a similar fashion, if you take R120, what would be the order of R120? It would be 3, because when you rotate the same circle by 120 degree, 3 times, you get back the angle 360, which was your original position, which is exactly equal to the identity element. Hence the order in this particular case is equal to 3, right? So here we have, hence we conclude, if we take rotations by different angles, say 360 by n, 360 divided by n, this is your angle, right? We have a rotation of how many of n, right? We have a rotation of order n, because in this case if you divide r 360 with 4, which is r 90, you have the order of this as equal to 4, correct? So this proves one part of the result, correct? So we have proved that it contains elements which are having finite order, and in fact every such finite order, correct? Now we wanted to show it also has elements of infinite order, and not just one element, it has many elements which are having infinite order. So let's talk about this issue. Does the elements of G have infinite order? The answer is yes. Does it have infinite order? The answer is yes. How? Let me demonstrate this to you. Let's have a look here. So this is your given circle, correct? This is our given circle. So in the circle, let's take this vertical axis, although it is not very much required. Now this is our initial position, which we call by r0, correct? Okay, now if you rotate this circle by very small angle, right? So in the clockwise direction, so if you move it by very small angle, you would have its order as very large. Why? Because if you rotate it by 360 divided by n, right, then its order is what? It is n. So that means when we want the order n to be very large, which is actually infinite, right? Say infinite. So we can make it by taking limits. So we may tend the angle, which is what? Which is 360 degree by n, to be very small, correct? So we may tend it to be very small. The angle tends to be very small because we can take the limit now. We want our limit n goes to infinity here, right? So that here we have to take the limit n goes to infinity only for r 360 divided by n. So this angle should approach what? Because n is in the denominator, the angle should approach 0, correct? Hence for very small angles, for rotations by very small angles, give you elements having infinite order, and this is what was required in our question, right? So I hope you understood this question well. That is it for this video. Thank you for watching.